Hi, my name is Kumar, and today I'm going to present our work on the topic investigating the ability of pins to solve Burgess PD in a finite time block. In this work, I collaborated with Dr. Anubit Mukherjee of the University of Manchester. Now, why pins are interesting? Pins have been achieving ever newer feats of solving complicated PDEs numerically while offering an attractive trade-off between accuracy and the inference speed. In the work that is cited below, they have shown for the first time that one can minimize certain empirical errors to find provably good approximations to any PD. So in this work, we investigate the stability of pins in a finite time blobs from a theoretically rigorous viewpoint. Now, why finite time blobs? Existing studies with pins, including studies of its failure modes, focus on cases where the true solution is nice. A finite time blob is a phenomena where the solution U becomes infinite at some point as t approaches to certain capital T, where capital T less than infinity. While the solution is well defined for all t between 0 and capital T, the supremum of u of x comma t, goes to infinity as t goes to capital T. For example, if you look at the ODE du by dt is equal to u square with the initial condition u naught, you will see that this solution blows up as t goes to 1 by u naught. Here we note that blow up is not a rare phenomenon. It happens quite a lot in real world. For example, if you look at the chemotaxis model, the thermal runoff model. In recent experiment that I have cited below, they showed that pins can possibly discover PD solutions with BlowUp even when their explicit descriptions are not available. Hence, inspired, we embark on a journey to understand this interface from a theoretically rigorous viewpoint and show how well the theoretical risk bounds correlate to the experimentally observed values in a certain BlowUp situation. In this case, we choose Burgess PD because we know a solution that blows up in finite time and we want to perform a control study, hence Burgess is a simpler case. Now we look at D plus 1 Burgess first. D is the number of spatial dimension, 1 the temporal dimension. On the left we have the PD, the right the initial conditions. If U theta is a neural net, we can define the conditional residual and the functional residual respectively. We define the L2 risk as L2 distance between the exact solution and the neural surrogate solution. In theorem 1, we provide upper bound for the D plus 1 Burgess, upper bound to the logarithm of the L2 risk. Here we want to note that C1, C2 does not need the knowledge of the exact solution, but we need to know the upper bound to the grad of U and the norm of U. We also want to note that the proof of the above one does not use divergencelessness and hence it allows for flexible boundary conditions. Similarly, we do analysis for 1 plus 1 Burgess where the PDs, the initial condition and boundary condition are defined respectively. These initial condition and boundary conditions correspond to the exact solution to the Burgess, which is U equal to x by t minus 1. This solution blows up as t goes to 1. Similarly, we define conditional and functional residuals, and theorem 2 gives an upper bound for the square root of the L2 risk in terms of residual and some constants. Here are the constants. Now, for the 1 plus 1 Burgess, we observe that the pin risk is stable in a very precise sense. That is, if pin risk goes to is order of epsilon, then that would actually imply that the L2 population risk is also order of epsilon. This definition of stability is defined in the paper that I cited below. We perform analysis on the 1 plus 1 Burgess for various values of delta. Here I have shown the plots for delta is equal to 0.998. Remember, the blow up happens at equal to 1. Now, we also plot the left hand side and right hand side of the bound for theorem that we have shown in theorem 2. We perform this experiment for neural network of 2 with 30 and with 300. We see that the collision coefficient increases with width and it holds up quite well even at very high values of delta. We perform similar analysis for 2 plus 1 Burgess. Similarly, it holds up much better for the correlation holds up much better for the width 100 than for width 30. It would be interesting to see if pins can be modified in a manner such that it's more sensitive to the local structures of the solution, since finite time blobs are a local phenomenon. Also, what we have shown the stability for the 1 plus 1 dimensional Burgess is not yet true for D plus 1 dimension. That would also be interesting thing to see. The same holds true for D plus 1 dimensions. Thank you.